Hello, everyone, and welcome to this webinar presented by Crop Vitality, which specializes in sulfur-based fertilizers, providing growers around the world with the crop nutrition tools they need to optimize growing conditions. With rising fertilizer costs and increased environmental concerns, protecting your nitrogen investment has never been more important. In this webinar, we will discuss continued research from Crop Vitality in Auburn University that has shown that thiosulfates used at higher rates can significantly slow the rate of nitrification when compared to commercially available nitrification inhibitors. Before we begin, I'd like to introduce our presenters. Dr. Zack Ogles is an Auburn University graduate with a master's degree in horticulture and a PhD in agronomy and soils. Dr. Ogles started his career with Crop Vitality in 2016 as an agronomist for the southeastern United States. Over the years, he transitioned to become the manager of agronomy, overseeing responsibilities throughout North America. Specializing in soil fertility and crop production, Dr. Ogles works with various crops and management systems, aiming to provide growers with sustainable and profitable solutions. His recent focus involves optimizing conventional and organic fertigation practices, including a pending patent for nitrification inhibition to address environmental concerns and economic losses in nitrogen use. Also speaking is Dr. Elizabeth Lemings, Crop Vitality's Midwest Regional Agronomist. Dr. Lemings completed her master's and PhD degrees in plant and soil sciences at Oklahoma State University, with expertise in nutrient management for crops like wheat, sorghum, corn, and soybeans. She oversees field trials and provides product support for the company's fertilizers. Dr. Lemings is dedicated to improving nutrient use efficiencies and exploring remote sensing applications in fertility management, aiming to deliver efficient solutions that benefit both customers and growers. Now I'm going to turn it over to Dr. Ogles to begin the webinar. Doctor?
Okay, thank you, Larry. I appreciate that. And today, really what we want to do is we want to go through and share with the group some of the research that we have conducted over the past several years now. In fact, this research began back in 2017 and is still continuing to this day. We still have projects that we're currently working on, looking at, again, the nitrification inhibition and just improving overall nitrogen use efficiency using our thiosulfate-based products. So just to start, what are thiosulfates and what are the products that we're discussing? So many of you are already familiar with our products like Thiosol or KTS or CAT. All of those are thiosulfate-based fertilizers. And what thiosulfate is it's a negatively charged ion. It's 2 sulfurs and 3 oxygens. And the way our products are produced, they are combined with different nutrients like potassium to form KTS, our potassium thiosulfate, ammonium to form our thiosol product, or calcium to produce our calcium thiosulfate product, CATS. So the interesting thing about thiosulfates and what makes those really special fertilizers is that they are in a intermediate state of oxidation. So if we look at this diagram here, you see thiosulfate on one side and sulfate sulfur on the other. So that process of oxidation has to take place in order for thiosulfate to become sulfate, which is the plant available form of nitrogen. Sulfur. So one of the things what's interesting about this product is that it does more than just provide fertilizer. These are liquid fertilizers that blend with other nitrogen sources or or phosphorus sources. But what's really the benefit is that they do other things other than just provide sulfur nutrition, which is, of course, very important. They can help lower the soil pH as they oxidize. They act as reducing agents, and we'll come back to this, but a reducing agent is something that as it reacts in the soil, it generates electrons. And those can have some major impacts on the availability of micronutrients in the soil. And that's one of the things that really is a great benefit of these products. And we'll show how that translates into nitrogen use efficiency and slowing down the nitrification process as we move further in the presentation. So how do thiosulfates bring value to a grower? Well, in a number of different ways. One, as I just mentioned, these are liquid fertilizers that can be blended with your other nitrogen or phosphorus sources and applied directly with the plants. So they can help increase your profitability, for one, by getting the most out of the nitrogen dollars that are being spent on a crop. You know, when you have a product like our fertilizer that can protect nitrogen, you're not only getting the value of the nitrogen that you're putting on the soil, on the crop, but you're also protecting nitrogen that could be lost to the environment. As we know, the application of nitrogen to certain crops has a direct correlation to the yield. One really important example of this is corn. Corn has a very linear relationship in increasing yield with nitrogen rate. And this carries all the way out to, you'll put a point where you have a diminished return of that, of course. But if you fertilize for a specific yield and you lose a percentage of the nitrogen that you're applying, that's money that's not going to go to yield, and it's not going to be realized by the farmer. So our products, again, they can help reduce your nitrogen losses and provide the full benefit of the nitrogen that's being applied. You know, one of our biggest benefits is the fact that these are sulfur-based products, and they provide high ratios of sulfur that in a liquid form. So in addition to protecting your nitrogen, you're also adding a soluble, readily available, once oxidation has taken place, form of sulfur that provides your crop with the sulfur that's necessary to maximize your yield. And last but not least is protecting the environment. Our products, by slowing down the process of nitrification, reducing volatilization, and increasing yield on a given piece of land, all of those things are major benefits for the environment. Nitrate leaching is, of course, a major concern for the environment. Ammonia volatilization is not only a loss for the nitrogen, but it's also, you know, a gas in the atmosphere that's detrimental to the environment. And of course, nitrous oxide emissions, and we have some research ongoing to look at that in a little bit more detail. So this is the nitrogen cycle is something that I think is important just to start with. And, you know, nitrogen is a complicated nutrient for the crop. You know, nitrogen comes from the atmosphere. It can be fixed by certain crops like soybeans or other legume crops from that atmospheric nitrogen. You know, it comes from decomposed organic material. It even can be from lightning events where you have nitrogen being produced in the atmosphere that eventually makes its way to the earth. One of the things about the nitrogen cycle is that there are many ways to lose nitrogen, one of which is leaching of nitrate nitrogen, the volatilization of ammonia from ammonium nitrogen, and denitrification from nitrate nitrogen. All these represent a significant loss for the farmer, and with our products and proper management, we believe that we can reduce those losses and have a positive impact on the environment. So plants take up nitrogen in these two forms, essentially, ammonium and nitrate. Now, I'll put the caveat with this, that there's a small amount of nitrogen that may be taken up in the form of urea and other nitrogen-containing compounds, but the vast majority of nitrogen is going to be taken up in one of these two forms, both of which have characteristics associated with them. Ammonium nitrogen, as you can see, has a positive charge associated with that. Nitrate nitrogen has a negative charge associated with it. So what that means is that positively charged ammonium is relatively stable in the soil. It's held by the soil colloids, and it is not easily leached in the soil. So it provides a stable form of nitrogen. Nitrate nitrogen is negatively charged, and that negative charge allows that material to be moved through the soil profile with rain events and through leaching. Another loss pathway for nitrate nitrogen is to be lost to the environment through denitrification, and that is essentially the reduction of nitrate into a form that can be lost back to the environment in the form of nitrous oxide gases. And this is obviously a concern in the fact that we're losing nitrogen that otherwise would go toward increasing yield, but also from an environmental standpoint. So ammonium, while it's stable in the soil, it also has one mechanism of loss that's significant, and that's volatilization as ammonia. Now, ammonium in the soil, as I said, is very stable. But when ammonia is on the surface of the soil and you have like higher pH, then you can have a shift from ammonium to ammonia nitrogen, which is very volatile, and it will be lost to the environment. Where we see this become a pretty significant issue is with either high pH soil, which shift that balance from ammonium, which is the form favored at lower soil pHs, to ammonia, which is more favored at high pHs. We see that a lot with, again, soil pHs that are high, or when we use urea forms of nitrogen. During the process of the urea hydrolysis, there's a spike in soil pH, or in that microsite pH, that causes the volatilization of ammonia. So those can be very significant losses. I mean, in some cases, it could be, 20% is not uncommon. So the positive thing about this is that thiosulfates can help reduce all three of these loss pathways. We've shown that our products can reduce ammonia volatilization. They can slow the conversion of ammonium nitrogen to nitrate, and that can reduce the amount of nitrogen lost through leaching, as well as the nitrogen that's lost through denitrification. So on the next slide, I'm going to go into nitrification in a little bit more detail and explain our hypothesis on how this is working, and get into some of the research trials that we've done with Auburn University and at our own research farm in California over the past several years. So when you see ammonium in the soil, you have an ammonium source of nitrogen, and that is going to be converted through a natural process called nitrification. And this is a more in-depth slide showing those different steps of nitrification. So as I mentioned in our second slide, when I was discussing the more the chemistry of thiosulfate sulfur, I mentioned that those are reducing agents and that they can have an effect on micronutrients, particularly metallic micronutrients like iron, zinc, copper, manganese. And we believe that is where we're seeing an impact on the rate of nitrification, is that the thiosulfates, they're not having a negative impact on the soil microbes. What we're seeing is that they are impacting the enzymes that are responsible for this conversion. So in the first case, we have the conversion from ammonium into hydroxylamine, and there's a enzyme responsible for that has a metallic center, the active point in that enzyme. Then the conversion from hydroxylamine to nitrite, again, an enzyme with a metallic center. And we see that those are likely being affected by the presence of thiosulfate, and they slow this process down. The reason I say that it is the first stages of nitrification as opposed to the conversion from nitrite to nitrate is because we see a buildup of ammonium in the soil, not a buildup of nitrite, which would indicate that there was a significant reduction in that last step. And we've shown this by literally thousands of samples that we've taken to establish the content of nitrite and nitrate in the soil. So let me skip to this next slide. So the nitrate pollution is a major concern, and that's something that we feel like our products can have a dramatic effect on. You know, nitrate is being looked at by many of the world governments, especially here in the United States and Europe. This has become a major concern based on groundwater contamination. This is really something that we have to pay attention to. I was going to show this map just briefly of the United States, and you can see some of our biggest agriculture areas are the areas that are most likely at risk of groundwater contamination. But we feel like that by using our products and the 4R method of crop management, we can reduce substantially the amount of nitrates that are escaping the root zone and ultimately ending up in bodies of water. So this is one of the data sets, and I'm going to focus on this set of data because this is a California soil. Both of these graphs were generated from lab analysis and soil extractions of this soil. And this was collected at our research farm in Dinuba, California, in the San Joaquin Valley. It's very representative of the types of soil that's in some of the most highly productive areas of the country. And what we have seen is that the rate of nitrification is substantially reduced by the presence of either thiosol or KTS. So I'll just direct your attention to the 2022 graph. As you can see, the y-axis is the amount of nitrate that is showing up in the sample, and the x-axis is the number of days after we made our initial treatment. So just to give a little bit of background on how this was done, we have small containers that were filled with 200 grams of soil, and we applied a rate of fertilizer containing either a nitrification inhibitor or our product, or just the nitrogen source alone, which in this case is a urea solution. So we applied that at a rate of 120 pounds per acre. And what we saw, we just allowed this to incubate at room temperature for a period of time, in both cases 70 days. So what we see is this initial response, the urea curve, which is this greenish color on the 2022 graph, we see a very sharp increase in the amount of nitrate. And that's what we would expect. You know, this is unprotected nitrogen, and it's going to convert quickly into a nitrate form. But now, when we start looking at the medium rates of thiosulfate, both KTS and thiosol, we see a substantial reduction in the amount of nitrate being formed. So all the way out to about 35 days, we saw very little being formed. And after that, we do start to see nitrification take place. Now, the purple line, that is a urea solution with the commercially available nitrification inhibitor, DCD. That product has been around for many years, and it works. And you can see that it's substantially reduced the amount of nitrate formed. But when you look at the higher rates of thiosulfate, which that's the green and the gold-colored line, they are very low, all the way out to about 55 days before we really started seeing hardly any nitrate nitrogen show up in the system. So very, very substantial reduction in nitrification. Now, if I could direct your attention to the 2023 graph, what we see here is very similar results. We see that, again, the thiosulfate treatments had the lowest amount of nitrification compared to either untreated urea, or in this case, we have urea with ammonium sulfate at an equivalent rate of sulfur. So both of those, both urea and urea with ammonium sulfate, both of those nitrified very quickly, and this is as you would expect from an unprotected nitrogen source. But again, we see substantial reductions in the rate of nitrification using our thiosulfate-based products, and we're using those at a rate that is comparable to what would be used in a typical production operation. So this is the same data, but I just wanted to point it out. I took this data from 45 days after treatment from both years and just combined them into one graph. And as you can see, the treatments that received either KTS or thiosol all showed a significant reduction in the amount of nitrate being detected in these samples. The urea and DCD, that also reduced nitrification just as you would expect. However, in almost every case, it was less effective than the thiosulfates, especially at the higher rate. And as you can see, ammonium sulfate with urea and urea alone, neither had any reduction in the rate of nitrification. So I've covered most of the work that we've done with nitrification over the past several years. And now I want to talk a little bit about volatilization and how our products can have an impact on that and how we're actually studying this to be able to quantify those results. So I want to show this piece of equipment that we have constructed out at our research farm. And what this piece of equipment does is it allows us to very accurately measure the amount of ammonia that is being volatilized off of each one of these soil samples. So as you can see, each one of these jars across the top, this has soil samples in there, and it has an air gap above that. And each one has air being passed across it using a air pump and these silicone lines that go to each one of them. That air that moves across the soil, it goes down into acid traps, which are lined up across the table, and that traps the amount of the ammonia that's actually being produced from each fertilizer treatment. So in a typical example, we have 16 containers here. We could do 4 treatments with 4 different replicates. So we would apply a specific fertilizer treatment into each one of these containers, and we would allow this to go for anywhere between 14 and 21 days to actually quantify the amount of ammonia that's being lost. So the first, we made a run for one of our international colleagues back a month or so ago, and we used a urea with thiosulfate, urea with NBPT, which is a commercially available urease inhibitor. It's one of the most effective on the market. Urea untreated, this urea alone, and then we did an untreated control. So what we can see from the graph is that again, the y-axis is the milligrams of nitrogen that was volatilized during the period of time, and the x-axis is the number of days after treatment. In this case, we went out to 14 days. So as you can see, the green treatment, which is the untreated urea, we had a significant amount of of ammonia volatilized from that surface-applied urea. The blue line, that was the urea with thiosulfate, and as you can see, it reduced that amount significantly. In this case, it was about a 45% reduction. You can also see the red line, that is urea with NBPT, which is, again, it's a urease inhibitor, and you can see it worked really well. It reduced almost entirely the amount of volatilization out to about 9 days. After that, it starts to, the effectiveness starts to decline. You start to see some ammonia being volatilized. But this does show that the thiosulfate-based products do have a very positive impact on the amount of ammonia being volatilized by surface-applied urea. And one of our other products, which I'm not going to show today, but calcium thiosulfate actually has really, really good results with this as well. But this is some of the most current data that we have available. So in this case, it actually is a statistically significant difference with the thiosulfate versus the untreated urea. So with that, I've discussed all the lab research that we've done, and most of what I've discussed has been done in a laboratory setting. But we know that it's really important to take that data that we've collected in the lab and see how that works in the actual field in a real setting. And so Dr. Lemings, I'm going to hand this off to her and have her go over some of the field research that we've done this year and how our thiosulfates have performed under those circumstances. Elizabeth?
Thank you, Zach. So as Zach mentioned, I'm going to share with you guys a little bit about our field research over the past 2 seasons. And really, we have that solid foundation of our findings in the laboratory setting. So now let's put it into practice and really see how it performs and ultimately what that means for profitability for our growers. So over the past 2 seasons, 2022 and 2023, we partnered with Twin State Incorporated, and you can see here in this central map, they're primarily located in eastern Iowa, kind of that northwestern Illinois area. So a lot of our locations in the field were in this central region. And really, as Zach mentioned, taking this to the field, we had 2 simple goals. So first, using kind of the methodology that we've already implemented in lab studies, let's implement that in the field, look at a few different rates of thiosulfates blended with UAN and how they compare to other commercially available products and how they respond in terms of yield. The second factor in the study was kind of getting back to that sustainability side, which he also mentioned, looking at the effect of adding these inhibitors or thiosulfates and how that can potentially reduce greenhouse gas emissions, especially in the form of nitrous oxide. So this picture here on the right is an image of a LICOR instrument. You can see we set those down on soil collars where that's able to measure those soil fluxes in real time, and we're able to get a better insight into what those emission factors are. So to begin, I'll go through kind of similar studies and results as Zach did. I'm now only looking at the field portion. So just taking a moment to kind of set up this image for you on our y-axis, you can see we're looking at nitrate, nitrogen, and parts per million. On our x-axis across the bottom, we're looking at these measurements over time. So essentially, we went out there and took soil samples in those fertilizer bands weekly for about a 2-month time frame and really monitored, okay, how much is in the nitrate form, what's in the ammonia form, and really monitoring those transformations in the soil. If we look at our legend across the bottom, this indicates our different treatments that we're comparing. So just to give you a little more clarity on what these mean. First, our yellow axis here is looking at UAN alone. So that's unprotected nitrogen. Next, we have our 2 thiosulfate treatments. So one including 15 pounds of sulfur from Thiosul, and the following one including 30 pounds of sulfur to the acre from Thiosul. Our light blue treatment then is our UAN plus a standard inhibitor, and then of course the check treatment where no nitrogen was applied. So in total we applied 180 pounds of nitrogen across all treatments, and then we looked at those differences. So if we go across time in the graph, we'll first look at our yellow line indicating our unprotected nitrogen. So again, we're monitoring those nitrate levels over time, and we're wanting to keep those lower, limit that formation so we have less susceptibility to lost pathways. And we can see that our unprotected nitrogen ended up with the highest overall nitrate levels. And then we look at our different thiosulfate treatments compared to an inhibitor as well, and those significantly reduced our nitrate levels in the soil. Next, I'll draw your attention to these rain events. So this is kind of matching up when rainfall occurred. So a key point here is to look at our date of the June 20th and looking at, when we had unprotected UAN, we were able to have more susceptibility to lost pathways. So we were looking at about 40 parts per million to lose if we looked at those rainfall events. And then in that later thiosulfate treatment, we lost only 75 parts per million. So again, significantly reducing the amount of nitrogen that was available to be lost through different loss pathways, but also could still be taken up by the plant. So again, not reducing plant available nitrogen, but reducing that availability to loss. So next, looking at, again, a similar graph, just another location from 2023. Again, those same treatments and measuring our nitrate nitrogen over time. So again, in this case, we are seeing similar results where our unprotected nitrogen or UAN treatment ended up with the highest level of nitrate susceptible to loss, especially when we consider when those rainfall events occurred. And as we watched that peak drawdown when those rainfalls occurred, we could see that the unprotected, the yellow bar, was more susceptible to loss compared to those treatments where thiosulfate was used or an inhibitor, so nearly reducing that potential loss by 50%. So a few key takeaways from 5 site years of data. Again, this research in the field has been going on for 2 different seasons, over 5 different locations, and in general, we've seen very consistent results that 15 to 30 pounds of thiosulfate sulfur was effective in slowing down nitrification for about 20 to 30 days. And again, that time window can vary depending on environmental conditions, when rainfall occurs, when temperature fluxes happen, but in general, that's a good standard practice to rely on. Next, if we look at our 30 pound of sulfur rate per acre, was generally as effective or more effective than commercially available inhibitors such as nitropyrin. So illustrating that yes, when we took this to the field, we were able to see very similar effective results. And then finally, I'd just like to point out that the application method of these blends really matters. So when we're talking about these applications, again, we're emphasizing the importance of banded applications. We want to make sure thiosulfate sulfur is in a high enough concentration in the soil to be effective in slowing down the nitrification process. So even when we're going into banded applications, it's important if we're doing one band next to that row, or maybe we're split dribbling that into 2 bands. When we do split apply those applications, we're reducing that concentration in each of the bands, splitting that into 2. So in those cases, you might want to consider raising your rate just a little bit more. All right, so now that we've looked through some of our soil data and illustrated that, yes, thiosulfates are effective in slowing down nitrification and being able to keep more nitrogen available for the crop, now we take that a step further and look at the overall impact on yield and ultimately profitability. So in this graph here, I'm illustrating the difference in change in grain yield compared to UAN alone. And essentially, what this means is, okay, over our 5 site years of data, what was that average response to our different treatments? And you can see across the bottom, again, we're looking at those same treatments where we use 30 pounds of thiosulfate sulfur or 15 pounds of thiosulfate sulfur, which equated to about 10 or 5 gallons per acre of thiosol blended with that UAN, and then compared it to UAN plus nitropyrin as well. So you can see here the importance of sulfur nutrition. So when thiosol was used, we on average saw an increase of 11 to 12 bushel per acre in yield. Now it's important to keep in mind that this nitropyrin treatment did not have a positive response to yield, but again, sulfur was not part of this equation. So what we're really focusing on here is the value that thiosol brings in terms of sulfur nutrition that's needed and leads to greater yields, but also its ability to slow down nitrification and protect nitrogen losses. So now if we take that even further and put, some dollars per acre behind this, and really what does this mean to the grower when they're penciling out their per acre profitability? So there's going to be an increased cost to any different management practice that you implement, right? So in this graph here, we're essentially looking at those same treatments, again, 15 pounds of sulfur, 30 pounds of sulfur, and then using nitropyrin and comparing these all back to a standard application of if we just did UAN by itself. And these are using most current pricing. Again, pricing is very fluctuating, so this can obviously change, but this gives us a snapshot of what it looks like in the current time. So first, we look at our UAN cost across our treatments, and again, using thiosulfates, we're able to apply a little less UAN because we get nitrogen with that product as well. Then we add in our thiosul cost per acre, which was $10 or $21 per acre, depending on the rate used. And then estimating a nitropyrin cost would be $12 per acre. So that brings our total of increased cost per acre of $6 to $13 to $12 per acre for implementing those additional products and additional practices. If we go down to the next line, then again, we're referencing those yield responses that we saw in the previous graph. So again, 11 to 12 bushel per acre increase when we use thiosulfate sulfur, or in this case, a negative response when nitropyrin was used. And then our increased revenue per acre, if we assume a corn grain price of $4.69 per bushel, we get an estimated profitability at 55 or 57-ish dollars, or a negative response in this case when nitropyrin is used. Again, sulfur was not a part of that treatment. And then finally, that brings us to our increased profit per acre, where we see $44 to $48 per acre increase by using thiosulfate sulfur, which again is giving you that sulfur value that you can always count on and you know is needed in your crop, and also the ability to protect nitrogen in the soil. And so finally, that brings us to our ultimate kind of measuring device, where we look at our different nitrogen use efficiencies of these treatments, right? And how efficient were these systems? So by implementing thiosulfates, whether that was 30 or 15 pounds of sulfur, again, around that 5 to 10 gallon per acre rate applied in a band. We're not talking about broadcast applications, but banded applications. We were able to improve our nitrogen use efficiency overall by 8 to 9%. So that represents, a significant increase to the grower's profitability, as we just saw in the previous slide, and also limits environmental loss. So again, relying on that sulfur nutrition that's going to be needed in these cropping systems to make, help the plant use nitrogen more efficiently and ultimately protect it in the soil, gives growers a lot of value and peace of mind. And with that, I'll turn it over to Zack for any closing comments.
Okay, thank you, Elizabeth. Just in closing, I just wanted to point out a few of the research projects that we're going to be carrying out this year. One of which is really looking at nitrous oxide emissions and looking at a carbon footprint associated with using our products and how we can help improve that. And of course, we have all this is directly tied to yield and making this profitable for growers. We want to make as big of an impact on the environment and have a positive impact any way we can, but we also have to keep in mind grower outcome and what's going to work for the grower. So we're going to continue to do that. We're also going to look at some different application methods, including fertigation and the use through center pivots, to give us a little bit better data set on what kind of results we can expect with those different applications. So with that, Larry, I don't know if we wanted to open it up to a few questions here. I think we have a few minutes for that.
Yes, absolutely. Thank you, Dr. Ogles, and thank you, Dr. Lemings. Great job, great presentation, very informative. And we do have quite a few questions here, so let's get to them. Dr. Ogles, let's start with you. What are the best application methods to maximize these benefits?
Okay, I'm glad that we have that question, because I just wanted to clarify that the way that thiosulfates work and the way that we have seen the most effect have been when they are in a concentrated band. So what that means is that when we have, like for example, if we're doing a side dress application, whether it be dribbled on the surface or if it's going to be knifed in, when that fertilizer is being applied, when the thiosulfate fertilizer, I should say, is being applied with a nitrogen source, it's concentrated in that band, that's where we see the most benefit. And the way we have a way we have learned to calculate this based on the parts per million of sulfur in that soil. And what we found is that when we have a part per million of thiosulfate sulfur in the soil above, say, 100 parts per million, that we start to see significant nitrification inhibition. When it's 200 plus, we see really strong nitrification inhibition. And just to go back, these are rates that are very common. I mean, we're talking, maybe 15, 16 to 30 pounds of sulfur per acre, which are both reasonable applications. I did mention some of the future research, which is going to be looking at fertigation options and maybe micro sprinklers or even drip irrigation. So in those type of applications, the product is our thiosulfates are not as concentrated. We have seen benefits, but we haven't been able to quantify those benefits. So this year we've got one trial already set up out at the Learning Center to try to evaluate this, but that's something we're going to continue to look at. So thank you for that question.
Okay. Thank you, Dr. Ogles. Okay, Dr. Lemings, we have a question for you. When you mix 28% UAN with thiosol, would you need to add in nitrogen preservation products?
Thank you, Larry. Yeah, that's a great question. So this really hones in on the results that we kind of presented today. So when we do blend that 28% UAN with thiosol, as long as we're banding it and we're getting that sulfur concentration, like Zach was just saying, in a high enough concentration, we feel pretty confident that we're going to be able to provide that same benefit that a lot of other commercially available inhibitors do. So again, it all goes back to the concentration in the soil and how we apply it. And when we're in those banded applications, like Dr. Ogles was mentioning, 15 to 30 pounds of sulfur per acre equivalent of thiosol would be pretty effective in doing that.
And just to add to that, the blend of UAN solution and thiosol, that's a very stable blend. So that could be made, well in advance and stored, and then still be able to provide those nitrification benefits.
Okay. Dr. Ogles, sticking with you here, where I have soils already with very low pH, will thiosulfate make this worse? Currently, we have pH as low to mid 4s, some as low as 3.8. Doctor?
Okay, so those are very low soil pHs, and so what we would want to consider is really the rate in which thiosulfates are going to be applied. At a high rate of thiosulfate, or if we use thiosol for at a high concentration, that would lower the soil pH potentially from the oxidation of the thiosulfate sulfur. Now, I will say this: if you have a pH that is that low, like say 4 or lower, the nitrification is not going to occur very readily because it's out of the preferred pH range for most of those microbes that make that happen. So I would say in that situation where you have like maybe for blueberries or something that just prefers a really low pH, it's going to have maybe even less of an effect on that extremely low pH, just because you're not going to be seeing a lot of pH reduction from the ammonium form of nitrogen that's with thiosol. I hope that answered that question.
Thank you, Doctor. Dr. Lemings, question for you. How would this compare to using other forms of sulfur, like ammonium sulfate?
Yes, that's a great question. We have different options of sulfur forms available, and not all of them are going to react the same way in the soil, right? So as Zach was explaining earlier in the presentation, how thiosulfate goes through that oxidation process to become plant available sulfate, that is where we're seeing this nitrification benefit happen. So in that oxidation process is where we're slowing down and interrupting some of those microbial processes in the soil, and therefore products like ammonium sulfate, it's already in that plant available sulfate product. It doesn't have to go through that same oxidation process in the soil. And he showed that in one of the lab studies too, that it doesn't have that same effect like thiosol. So it's essentially, the same as unprotected nitrogen. So be mindful of your sulfur sources and recognize that this is something that's specific to thiosulfates.
Thank you, Doctor. Dr. Ogles, back to you, sir. What is the recommended ratio of UAN to ATS, I used not a ratio of 9-to-1 gallons for years. Maybe I need to increase the ATS? Doctor, your thoughts?
So that's a good question. One thing that we have seen is that when a 28005 is an analysis of UAN and thiosol that's extremely common throughout the Midwest. What we have seen is a move for people to use a higher rate of thiosol with their UAN, and what that does is, one, it allows the sulfur rate to be increased just to provide the nutrient value of the sulfur. But what it also does is, by increasing just slightly the amount of thiosulfate sulfur that's going to be present in that banded application, it can have a really strong impact on the rate of nitrification. So by increasing it, just marginally, you can see a pretty clear increase in the effectiveness.
Okay, thank you, Doctor. Dr. Lemings, back to you. You mentioned banded applications. Can you address applications with Y drops using thiosulfates and UAN?
Absolutely. That's a great question. So again, when we're talking about those banded applications, that kind of goes back to, again, the concentration in the soil. So multiple bands or split bands in the case of Y drops, where we're, dividing that band in the soil, we're going to be mindful of the thiosol rates simply because we're splitting that band, right? It's not one single band against the row. So in that case, we may want to raise those rates closer to that 30 pound per sulfur per acre rate, or maybe a little more, just to ensure that longevity of the nitrification inhibition properties. But in both cases, really effective. Just be mindful of what rate we're using.
And just, Elizabeth, if I could, just to add to that, one thing that we spent the majority of the time talking about the nitrification inhibition benefits, but when you have something like is very popular, and I'm in Georgia, so one of the very popular application methods is a dribbled on application. That's concentrated in a strip right along the surface of the soil. Now, when you have thiosulfates, again, they're applied in that concentrated band, you're going to see benefits from nitrification inhibition. But if you're making that application and you have a product that contains urea nitrogen in there, so you can actually see dual benefits, which is the benefit of having nitrification inhibition to protect that nitrogen from leaching, but you can also see a benefit from reducing volatilization, having it been on a surface application.
Okay, thank you, Dr. Ogles. And another question for you, Dr. Ogles. How were the nitrate concentrations measured in the field studies?
Okay, so the way that we did the nitrate analysis in the field and in the lab was, what we did is we collected a sample from the soil. In this case, it was sampled in the what I'll just say the retention zone where the fertilizer had actually been applied, and we take those samples. They are taken back in a refrigerated container into the lab, and then they are extracted using a potassium chloride solution to extract the nitrogen from the soil. And then those samples are sent to another lab to be analyzed for the amount of nitrate and ammonium that is present in those soils. So we take the samples from the field, and then they ultimately are sent to a lab to where they do the complete analysis.
Okay, thank you. Dr. Lemings, what tank mixes are good or have concerns for compatibility for mixing with thiosol?
Absolutely. So again, getting back to our products, being thiosulfates, and again, we have, thiosol, ammonium thiosulfate, KTS, all of these products are generally going to be applied in a blend, right? We're not going to go out with that product alone, and we want to make those well-rounded nutrient blends. So When we talk about Thiosul, it blends very well with UAN solutions, both 32% and 28%. You don't have to worry about any added water in those cases. Now, if we talk about KTS in this case, so again, it having that same thiosulfate molecule, again, we've seen similar results with that product as well in terms of protecting nitrogen and reducing or, slowing down the nitrification process. We can also blend that with UAN, but we do need to be mindful of adding a little bit of extra water in there just to keep that in solution. So as far as Thiosul and UAN goes, we have great compatibility. If we add KTS into those UAN blends, we need equal parts weight by water of KTS and water in that solution to keep it suspended.
Okay, thank you, Dr. Lemings. Dr. Ogles, any studies planned to evaluate if nitrogen rates could be reduced if Thiosul increases in UE?
Yes, that's a good question. And so what we've looked at, obviously we're looking at increasing yields by improving nitrogen use efficiency. But you could look at that from another viewpoint, is that could we reduce the amount of fertilizer that we apply and get the same yield? And we are looking at that this year. As I mentioned, some of our future plans are to really start looking at the environmental impact of our products and the way that they're being used. And that's one of the ways that you can significantly reduce your carbon footprint as a grower, is by being able to reduce your fertilizer inputs. And so we are going to be evaluating that this year at our learning center. And hopefully by the end of next season, we would have some data to support our hypothesis that you could potentially reduce fertilizer inputs and maintain yields. But again, we don't know that right now, but we're going to certainly work to find that answer.
Okay, thank you. And Dr. Ogles, one final question for you. What rate of DCD was used in comparison?
Okay, so when we, in the lab studies that we did with Auburn, we used the labeled rate of DCD, and we got that from one of the commercially available products out on the market. And we didn't use so when we did the study, we did not use an existing product. We actually used the technical material that we sourced from one of the lab supply warehouses, but we used a rate comparable to what's recommended from the commercially available product.
Okay. Thank you, Doctor. Well, that about does it for our questions. We had several of them. We want to thank the audience for sending those in. Appreciate it very much. And that pretty much brings us to the end of our presentation. I want to thank everybody for attending the webinar, and I want to thank Crop Vitality for presenting it. And thanks to our speakers, Dr. Zack Ogles and Dr. Elizabeth Lemings, for an excellent presentation.